Alrighty, this is going on page 78 when we're done, and we're all going to pay very close attention and be good boys and girls because this is our last topic. Woo! And then we're all going to be on review, okay? Yay! All right, so we did volume with cross sections, right? With the triangles, the squares, the whatever. So when you want the volume of something, what do you integrate? Area. So if I want volume, I integrate area. Okay. So instead of having cross sections, we're going to think of taking something and rotating it. Okay, so let me see if I can draw you a not so great picture. You don't have to draw this, but if I have, let's say, a triangle in the first quadrant, okay, and I'm going to take this triangle, which looks like this, and I'm going to rotate it three-dimensionally, so I'm going to revolve it, actually. This triangle is going to come up off the board, rotate around, revolve around the axis, and then come back around and meet up. You ever seen those, like, Christmas bells and stuff that have I think it's called honeycomb paper? You, like, open it, they're Easter eggs, they're, like, flat, you open them up like that. It's kind of like that, like taking that and revolving it around. So if I do that, I would end up with a cone, okay? So see how you take that triangle, and it revolves three-dimensionally, comes off and behind the board, and you get a cone. Does that make sense to you? So that's the kind of volume we're going to find now. Instead of doing cross sections, we're going to actually take these and we're going to revolve it around. Now, if I did take cross sections here, wherever I took my cross sections, then I'd have circles, yes? And basically, if I stack up all those circles, that's going to give me the volume. So that's where we come up with like a flat disc. Like if I sliced it up, it'd have a little bit of thickness. What if I had this, and I have a triangle here, okay? Still going to revolve it around the y-axis, not around the side of the triangle, but around the y-axis. So then this would look like this. You kind of see that? Where it's like a cone that has the head chopped off and a cylinder dug out of it. Kind of see how that goes? So this time when we slice, so if I slice this, it's going to look like this, right? That's going to be my cross section. If I take a slice of this, it's going to look something like this, like a donut, okay? But what we call like the disc and the washer. That's why you have this Lifesaver. This is like a washer. In case you don't know what a washer is, not like the thing you clean your clothes in, but if you have nuts, bolts, and washers, you know what a washer looks like? Like if we're going to play the game of washers, they're like flat metal things, okay? All right. So they kind of look like this. You never played a game with washers? It's just like, it's like cornhole, but washers instead. So they can be really small, they can be really big. Like they come in all sizes. Yeah. There's that too. Whatever. Okay, so back to this, because I figured that was probably the easiest way to kind of show you what was happening, because unfortunately, like if we actually used those figures, we could find it using the math, because that's what you should have done in geometry. I did a ton of those when I taught pre-AP geometry, because they're actually pretty cool. But you should have at least done some of it. I don't know, but we won't have those discussions. It's okay. So here we have volumes of, we're going to talk about the discs first. So like just the normal old cone that we had. Since it's a disc, it looks something like this because it actually has some thickness. That is terrible. Oh my goodness. All right? Because there's some thickness to it. When you take a cross section, we're thinking circles, but just like I told you with the paper, if we stack them all up, what are you laughing at? What are you laughing at? Oh my God. Y'all are mean. Hey, I know, I want to laugh too. Have enough respect for me to tell me. I don't care if you're laughing at me, just tell me what it is. All right. So volume we integrate area, right? So we're going to find the area of the cross sections, which is the area of the discs that you would have there. Area of a circle is pi r squared. Okay? And we just integrate from A to B, whatever those happen to be. Another way you can write this, we can take this pi and we can factor it out of the integral so we don't have to worry about it. The integral, or pi times the integral from A to B of r squared dx. Okay? We all okay with that? Don't forget your dx. All right. So then washer, that was the other thing. That's your lifesaver that you have in front of you, because I wanted you to have something real in front of you that you could understand how that worked. And my picture's going to be terrible, but you can draw a better lifesaver, knock yourself out. So this right here is the little radius, because I need to take into account the little radius of the circle. And then this is the big radius, capital R. So for that lifesaver, you have to know the radius of the entire piece of candy and the radius of the inside missing part. And to find the area of that, okay, because you have something that actually has some volume to it, but to find the area of that, you would find the area of the big circle minus the area of the little circle. Does that make sense to you? Okay? We good with that? Capital R's for the big circle, lowercase r's for the little circle. So we could also write this as, factor that pi out and have integral from A to B of big R squared minus little r squared dx. Everybody okay with that? All right. This is actually going to be a little bit easier than with the cross sections because you don't have to worry about having different area formulas for all the different things here. All right, so we want to find the volume when f of x equals the square root of x from 0 to 4 is rotated about the x-axis. Okay, so we need to graph that. You should know what the square root function looks like. What does it look like? Yep, like that, okay? If you don't know, then you might have to plot some points and figure it out. This is what it should look like. Something like that, right? We're going to take this function from 0 to 4. So here's 0. We can make 4 right here, wherever we want it to be. And we are going to revolve it about the x-axis. So we want to make sure that we're using the correct axis. So it's going to revolve around like that. Okay? So it's not going to make a shape that we necessarily like really know what it is or how to name it, but you can kind of describe it, right? So if the way you draw these is you take it and first of all you reflect it in the axis that it's in. So it kind of makes it look like a parabola, right? And then we are going to revolve it around there like this. So it's kind of like a bowl. Yeah, well, except the bowl would not be kind of wobbly because it doesn't really have a flat bottom, but yeah. Yeah, something like that. And honestly, if you can't really figure out what it looks like, it's not the end of the world. But there are some things that we have to figure out. So what's happening here is we have got this is a disk kind of situation. I cannot even draw an oval. This is a disk kind of situation like this, right? Where this is my radius. Yeah. So how do I find the radius? 2. Okay. The radius right here is 2. You're 100% right. What's the radius right here? What's the radius right here? What's the radius right here? But how would we find it? Square root of x. Exactly. So the y values of the square root of x, that is my radius, right? So here r equals the square root of x. Okay, everybody good with that? Because the radius is the distance from the function to the x-axis, which is just the y value, right? So it's just the square root of x, no biggie. Okay, so that means that my area, right, is pi r squared, which is pi times the square root of x squared, which is pi times x. You agree with that? That is the area of any little disk that we would get. So if we want volume, we integrate area. So I'm going to integrate from 0 to 4. I can put the pi outside here, and this is x dx. We all agree with that? This is volume. Any questions at this point? Can you integrate that? Yeah. This is going to give me pi times, what do you get when you integrate x? X squared over 2. Do I need a plus c here? No, because it's a definite integral, because I'm about to evaluate it from 0 to 4. You with me on that? Which one do I substitute in first? The 4. So this is pi times 4 squared over 2 minus pi times 0 squared over 2. Do I have to do anything else? No, so don't. What the heck? There. I don't even know. I don't even think I touched anything. I don't know. Okay, but if I had some more information and I had units, I need units on it. So I would have this whole thing, and it would be units what? Cubed. Okay. Everybody okay with that? What questions you got? All right. Let's look at the next one. I'm going to find the volume when that same function, so let's graph our function. When this same function from 0 to 4 is rotated about y equals -1. So I am regretting where I drew my picture. I'm going to move it over some so I have more room. Okay. So this, here's my function. Actually, I didn't need to move it over, but y equals -1. That is not the axis. That is down here. Right? So we could say that this is y equals -1. So when you reflect this, okay, let's go back to our geometry days. I'm going to start by reflecting it in this line, which means if it's this far away from the line here, it's got to be that far away from the line over here and look like that. Okay, does that make sense? I need to be able to fold it on that dotted line and it match up. That's how a reflection works, okay? Because I see all kinds of weird things happen with reflections when it's not on an axis or when it's not touching it. Okay, so then when I do this and then I revolve it, so this is what the area that I had. Then I have this. Ooh, wait a second. Now it's kind of like a bowl, yes. So I have this area. This is what I have here. So I have this and I have that, and then it would be a really bad bowl though because, yeah, it has a hole in it. It's a broken bowl. Yeah, it's a bowl with a hole in it. My picture is really, really bad. I apologize. Do you kind of get the idea, though, from my bad picture? This is, yeah, that looks terrible. But what we have here is we have a washer, right? So we have this washer. It looks like this. You don't have to be an artist, right? There's your lifesaver, yes. So this is little r, this is big R, right? So little r and big R. What is your little radius? 1. This is your little radius right there. It's 1. Everybody okay with that? You good? Ask me a question. Okay. I know, my picture's terrible. Yeah, I know. I'm sorry. Okay. I'm really, really sorry. It's bad. Then I need the entire radius. What do you think? Square root of x plus 1? He did sound very confident, didn't he? This is the entire radius, right? From here to here we know is the square root of x, and what is this? 1. So it is definitely square root of x plus 1. Good job. All right, so remember what our little, now we can figure out the area, like the other one we just went ahead and figured out the area, but our rule here is this. Let's start right here. I'm going to integrate from 0 to 4. I can put the pi outside my volume. And it's big R squared minus little r squared. So my big R squared is the square root of x plus 1 squared minus little r squared, which is 1 dx. Yeah, 1 squared. Everybody with me? When I square that, we need to square it out, so we get pi integral from 0 to 4. When I square that, I don't just square both of them. We know that, right? You end up with a trinomial. Okay, it's like doing the square root of x plus 1 times the square root of x plus 1, just reminding you so you're not making up math. Okay, so when I multiply the square root of x times the square root of x, what do I get? X. Square root of x times 1 is the square root of x. 1 times the square root of x is the square root of x. So that gives me plus 2 square roots of x. 1 times 1 is plus 1. Then I can't forget about this guy, minus 1 dx. Everybody with me? Yes, yes. Okay, these ones zero out, right? And then I need to integrate. Can you integrate that? I'm going to have pi times, all right, when I integrate x, what do I get? X squared over 2. Then 2 times the square root of x is really like 2 times x to the 1/2 power, right? So I can write down plus 2 times. So if I think of that as x to the 1/2 power, I do what? Do I multiply by 1/2? No. I'm doing the integral. I'm doing the integral. Oh my God, I almost wrote the square root again. I can't even. X to the 1/2 power. That's what we actually have there, right? So I add 1. Here's my 2. I add 1 to the exponent. What does that give me? 3/2. And then I divide by 3/2, which means I multiply by 2/3 times x to the 3/2 power. And then I evaluate that from 0 to 4. Everybody okay with that? All right, so I'm going to erase this now so I don't get it. Just wanted to make sure we're thinking about it. You don't have to erase yours. I just don't want it to get mixed up in my other mess over here. So this is going to be equal to pi times. So I put in 4, and I get 4 squared over 2 plus 2 times 2/3 times 4 to the 3/2 power. Then I would have to subtract out the rest, right? But when I do that, do I even have to do anything else? If I put 0 into here, isn't this going to be 0? And 0 into here, that's going to be 0? So there's really not even anything to subtract. Even here, I didn't necessarily have to write that. I could have left that part off right there and been totally fine because it all just zeroes out. You with me on that? As long as there's not just a whole number or something in there or a constant, then you're good. So then, do I have to do anything else? No. So should I? No. Leave it looking nasty with the 2 times 2/3 so you don't make up something, okay? Leave it like that. You got units cubed. You are done. Okay? Leave it. We good? Are you capable of simplifying that? Yes. Do you have to? No. Therefore, do not. Okay? We're going to be safe with this. Okie dokie. Flip it over. Let's look at some other funky pictures here. We are going to find the volume of the solid formed by revolving the region bounded by, oh, look, this same function, but now we have another function, and we're revolving it around this line. Getting a little crazy, okay? So what gets weird here is not really the math, it's more just this, you using all this stuff to figure out what the radius is so that you're thinking about the picture correctly. All right, so let's graph this. I've got the square root function, and I've got just a plain old x squared function. So it looks something like this. Okay. And I'm going to revolve it around the line y equals -2 down here. So this is the little piece that I get. This weird kind of, I don't know how you even describe that. What? More shapes? Yeah. How would you describe that? What does it look like? I don't know. A bean? Kind of, I know. Piece? I was kind of thinking piece too. Oh, it's kind of football-y. Yes, it's not kind of like a long, skinny football. Okay, we'll go with that. So we're going to reflect that down here. When we do that, and you don't have to reflect the whole thing, but maybe it's easier for you to do that, is I can reflect this, and then I can reflect that. They're not exactly the same size in my picture, but it's okay. All right. And to me, it's easier to do the whole functions instead of just trying to redraw that shape because it would look even worse than it does. But I have this. Okay. So then when it revolves, this revolves here, this here, and then so it's kind of looks something like that, but a whole lot better. Mine always look absolutely terrible. Is this a disc or is it a washer? A washer or a lifesaver, right? However you want to think about it. And it looks like this, right? Okay, so what is the little radius? You sure about that? I would agree that well, shoot, that this kind of looks like maybe 2, but look at this. Oh. So it is whatever this y value is plus 2, right? How do I figure out what this y value is? X squared plus 2. Do you see that? All right. The big R. The big radius from here to here. Square root of x plus 2. Because this is the center of that circle, right? It goes to the outside of this square root function. So this is the square root of x plus 2. Everybody okay with that? What questions you got? All right. Good deal. Then let's see if you set up the integral. Then we'll check ourselves. Do you know what your limits of integration are? Where are we going to start? We're going to start at 0, right? So our volume, this is pi times, okay, we're starting at 0, but we don't know where to stop, right? But where we stop, how do I figure out what that is? Set them equal to each other. So I'm going to set x squared equal to the square root of x. Okay? I need to get rid of that square root, so can I just go ahead and square both sides? Get rid of my square root? Does that seem legal? Seems legal. So this gives me x to the 4th equals x. Here, can I divide both sides by x? That's a hard no, okay? Because you lose a root. That's bad, bad. But I can set this equal to 0. So x to the 4th minus x equals 0. Then I can factor it, and I get x times x cubed minus 1 equals 0. So I have two zeros. One at x. I got x equals 0. Well, that makes sense because we could tell that without doing it, right? And then I've got x cubed minus 1 equals 0. So x cubed equals 1. So x equals what? 1. So we're integrating from 0 to 1. Well, ask me a question. What? This? It's x cubed because I had x to the 4th, and then the cube root of 1 is 1. Okay. Then I got my big R squared, square root of x, plus 2 squared, minus my little r squared, x squared plus 2 squared. What am I missing? Dx. And we don't have enough room to do the rest, so. All right. Questions? All right, so I want you to sketch this, same graphs. We're revolving about something different. See if you can get that drawn and figure it out. Uh-huh. Uh-huh. The little radius. Okay, because the little radius is going, this is like the center of the inside circle, right? And it goes to where it hits this function right here. Yes, yes. Mm-hmm. Good question. Oh yeah, you can eat your candies now. You can have both of them now. I just wanted you to at least have one to look at a lifesaver while we thought about it. I think you get it now. You can eat them all. An x equals line, is it horizontal or vertical? Vertical. Okay, good job. So that means I'm going to make this a little bit longer. And so we know now that this is 0, this is 1. And so here's going to be my line that's x equals 2. And again, you can try and just reflect the little piece if you want to. Again, mine would look horrific. So I'm going to reflect the entire thing and then just shade it in. So if I reflect that, this ends up like over here. I don't even need to do the whole thing, but I can at least, oh, I can't even do that right. Can at least get like that. And then when I reflect this over here, it's going to look kind of like that. And then that's my other little piece there. Which makes this my shape like that. It's a bowl with a hole in it. None of these bowls are actually functional because the hole goes all the way through. That would be really bad. All right, so we have a washer. This time the washer looks like this. Right? So my little r is here, and this is my big R. And this time, they're not going to be in terms of x, they're going to be in terms of y, right? So this function that was y equals the square root of x, if I solve for x, I actually get x equals y squared. So this is x equals y squared. This one that was y equals x squared is actually x equals the square root of y, and just the positive one. Okay? So this is x times the square root of y. Not x times the square, oh my god. X equals the square root of y. Everybody okay with that? Because we're revolving this way this time, so just like with the cross sections, we had to take our functions and redo them so that they're solved for x and not solved for y. So if you have a horizontal washer or disc, you have to change it so everything's in terms of y. Okay? We good? Maybe? Okay. So then let's think about our little r. Okay? This little radius, which is this right here. Okay, that's my little radius. To go from here to here, that length is 2. But it's only 2 right here, right? I need to take this part and do what with it? So this is 2. Would we agree with that? Then are these bigger or less than 2? Less. So I need to take 2 and subtract this part out, and that part is the square root of y. So my little r is 2 minus the square root of y. Questions? Okay. Then our big R, which would be from here to here. Right here, again, that's 2, yes? Is this more or less than 2 as I go up? Less than 2. So I'm going to take this part, take 2 and subtract that part out. That's the y squared. So this would be 2 minus y squared. I know that when we start changing things to y's, it gets a little bit weirder. And it's not so much about the picture even, it's more about just understanding what's happening with the y's. So ask me a question. You've got a question. Just processing. Okay. Can you set up your integral? Okay. So let's try to set up the integral. Volume equals pi times the integral and we're going to go from 0 to whatever this is. What is this? It's 1. Because even though we didn't actually solve it on this one, it's the same. The things basically just kind of traded places. And so we end up solving the same thing. So we're going from 0 to 1. Big R, which is 2 minus y squared, minus little r, which is 2 minus the square root of y. Then what do I put? dy, because it is a y. Yes. I think maybe I said it. I don't know if I said it or not, but our big R squared minus little r squared. Okay, I don't know if I said it and just didn't write it or what, but we good? Maybe? dy, yes. Okay. We good with that? I don't believe you, but okay. But I'm going to stop today. You got 5 minutes left, but I don't want to burn your brains anymore. Oh, happy birthday!